Calculating eigenvectors and eigenvalues. I thought I'd do a quick video on just how to calculate eigenvectors and eigenvalues from square matrices. So first of all, let's work through an example and then we can have a look at the general method. So if we have an example of finding the eigenvalues and eigenvectors of A, where A is the matrix 2, 3, 3, -6. So the first thing we're going to do is we're going to solve an equation which is going to be the determinant of A minus lambda I equals 0. So we've got A. Lambda I is going to be lambda times by the identity matrix, and here the identity matrix is going to be a square with size 2, and that is going to be lambda naught lambda. Now obviously, because we're taking away, we can make that negative. That simplifies our life. So A minus lambda I2 is equal to 2, it's going to be 2 minus lambda naught, sorry, not noughts, is that? They should be 3's, and then -6 minus lambda. Now we want to find the determinant of this matrix, and that is going to be equal to 2 minus lambda lots of -6 minus lambda minus 3 lots of 3. So all I've done there is multiplied that one with that one, and then multiplied the two 3's together, and that is our determinant. So obviously from here, move this up, we want to multiply out this bracket, and that gives us lambda squared plus 4 lambda minus 21, and we wanted to solve that the determinant is equal to 0. So if we solve this for lambda, being a quadratic, it's easy enough to solve this particular example using factorising. So we can have lambda plus 7 lambda minus 3. So therefore lambda equals 3 and minus 7. Now, the one thing I haven't mentioned is what we've actually worked out here. So what is lambda? Well, lambda here is our eigenvalues. So our eigenvalues here are 3 and minus 7. So that is the first half of the question. So we wanted to find the eigenvalues and eigenvectors of A here, and we've worked out what the eigenvalues are. So if we just bring that up to there, higher, and then I'm just going to write out what A was again. So now we want to find out what the eigenvectors are. Eigenvectors. So to do this, we are going to solve another equation. This time the equation is A minus lambda I lots of the vector x is equal to 0. So we had our matrix A minus lambda I, where I is I2, and that was 2 minus lambda, 3, 3, -6 minus lambda. And we want to multiply that by the vector x, where we have x is equal to x1, x2, and here I forgot to say that 0 is the 0 vector, so that'll be 0, 0, because a 2 by 2 matrix multiplied by a 1 by 2 vector, column vector, is equal to a 1 by 2 column vector. So now all we have to do is multiply this out. But we actually know what lambda is now. So we can take this for the two values of lambda. So lambda equals 3 and lambda equals -7. Let's just do that lambda again. Okay. So split this up. We will solve this. So for lambda equals 3, first of all, that will make our matrix equation into 2 minus lambda, which is -1, 3, 3, -6 minus lambda is -9. x1, x2 is equal to 0, 0. So from here we can multiply out. So we're going to get -x1 plus 3x2 and 3x1 minus 9x2 equals 0, 0. And that is basically the two equations that 3x1 equals 3x2 equals x1 and 3x1 equals 9x2. So this is just the top row. Imagine we put an imaginary line in here. That's two different equations. And we can solve these simultaneously. If we take 2 and take out the factor of 3, we go at x1 equals 3x2. But that is the same as the first equation. So that means we don't know what x1 and x2 are going to be explicitly. So our first eigenvector, x1, is going to be the point where we have x2, 3x2, and this is a set of different column vectors. We can also write the same set as a constant times by 3, 1. So that is the same set of vectors, and because we just want to find one eigenvector, we can select any constant c, and for simplicity we're going to let it equal to 1. So our eigenvector for the eigenvalue lambda equals 3 is 3, 1. Now if we do the same thing for lambda equals 7, then what we're going to get is our first equation is going to be 2 minus lambda, 2 minus -7, which will be 5. Sorry, 9. Head isn't working. Then 3, 3, -6 minus -7 is 1. Lots of x1, x2 equals 0, 0. Multiply that out. 9x1 plus 3x2 equals 0, and 3x1 plus x2 equals 0. Now if we take the first equation here, we've got x2 equals -3x1. So I've just taken away the 9x1 and divided the whole equation by 3. Equation 2 becomes 3x1, and then we've got x2, so we're going to sub in equation 1 here. So it's going to be -3x1 is equal to 0. Now this doesn't tell us anything, which implies that we're going to have another implicit value for our second eigenvector. So therefore x2, so our second eigenvector, is going to be x2 and minus 3x1. Again, we can rewrite this as a constant. I'm going to call it C2 now to avoid confusion. Lots of one second, I've made a mistake. Here that should be the other way round. I've written it wrong. Apologies. So that should have been x1 negative 3x1, which then we can take out our constant 1 minus 3. Again, letting C2 equal to 1, we can have our eigenvector is 1 minus 3. So as a quick recap, what did we do to do this question? So the first thing we did, number 1, was we found the eigenvalues. And to do this, we had to solve the determinant of a n minus lambda I n equals 0 for lambda. So lambda is our eigenvalues, and we had to solve this equation. To find the eigenvectors, we had to solve the equation an minus lambda in, lots of the column vector x is equal to the column vector empty set 0 for x. And here we had to do this with lambda, the different values of lambda, I for I equals 1, 2. And that would give us xi. And that is calculating eigenvalues and eigenvectors. Thank you.